Hello, class. Welcome to lecture one of probability and statistics. So today we're going to be talking about outcomes, sample spaces, and events. But first, sort of the big picture goal of the class is we want to study probability, of course, because that's the name of the class. But not just in the way that you've learned before, where you just calculate probabilities of things happening. We want to do it in a very formal and mathy way, so using math language. But of course, that should match our intuitive understanding of probability. So like the probability of rolling a 3 on a dice roll should still be 1/6, even when we introduce all this formalization. That kind of stuff shouldn't change. We just want to say it in a way that makes everything very precise. Okay, so let's just jump into an example and see how it goes. Okay, so first let's consider what I just said, rolling a 6-sided dice. So in this class, what we'll call this type of thing is an experiment. So it can be pretty loose. It's just something that you do that has outcomes. Okay, so we call the possible results of the experiment. We're going to always call those outcomes. So when you roll a dice, there's 6 outcomes, and they encompass all possible things that can happen. When you list them, you don't randomly skip some, you write them all down. And what we do is we write them as a set. Which is a fancy math word that you learn about in a different math class. But it really just means that you stick them inside of curly braces. So you write these curly braces and you put your outcomes in here. So what are the outcomes of rolling a dice? They're rolling a 1, rolling a 2, rolling a 3, 4, 5, or 6. So the outcomes are listed in the set, which means they're in curly braces. So you could, if you want it to be very wordy, you could write roll a 1, roll a 2, and so on, roll a 6. But it's understood that just by writing the numbers 1 through 6, you mean that the outcomes of the experiment are rolling a 1 through 6. So there's no need to write all these words. Okay, so then when you write down the set of outcomes, that also has a name. It's called the sample space of the experiment. So here, the sample space of rolling a dice is this set. If you want to be less wordy, or you could write the bigger one. But it's this set with 6 things in it, the numbers 1 through 6. That's the sample space of the experiment, rolling a dice. But what we like to do is name these things. We name sets in general, or in this case, the sample space. So in this case, I can't spell. In this case, the sample space. So we can easily refer to it later. Right? I don't want to always, whenever I'm talking about this sample space of numbers 1 through 6, I don't want to have to write it down every time. It takes too long. So what we do is we say, I'm going to name it by writing that it equals something. And typically we're going to use omega. This is a capital omega. And you just say it equals the set to say that you're naming it that. So we've named the sample space omega so that I can refer to the sample space more easily without having to write down all the numbers every single time. And then we use notation from that other subject, set theory, in that other class that you learn about when you learn about proofs and stuff, like this one. So if I want to say something is in the sample space or in the set more generally, we can write this. So this is the notation. So for example, what is something that's in here in the sample space? I don't know, the number 5. So I can say 5 is in omega by writing this. So this means 5 is, and then in set theory, they write the word element to mean something that's in the set. So you would say 5 is an element of omega, or in our language for this class, I guess it would be more like 5 is an outcome of the sample space, which we've named omega. So then you could also say something like this. 27 is not in there, right? It's not one of these 6 things. So I could very shorthand way, I could say 27 is not, by writing is and then crossing it out, omega is in omega. It's not in omega. Okay, so this is just some notation that we borrow from set theory. So 27 is not an element of omega. So we're going to be using this kind of notation a lot in this class, so you got to get used to it pretty quickly. So let's do some more examples to help us with that. All right, let's do a different experiment. So if the experiment consists of flipping, so we're going to be flipping 2 coins, but really like one after another. And we record the results. Then what's going to be the outcomes and what's going to be the sample space? Well, this time the outcomes are not really numbers, but I want to still be able to write them down. So what I could do is say the first coin could have been a heads, and then the second coin I'll just write right after it. So this indicates that we flipped heads, then heads. So then what are the other possibilities? Well, I could have flipped heads and then tails, or I could have started with tails and then got heads, or then I could have got 2 tails. So these are the 4 outcomes. And then what's the sample space? So I am going to be very nitpicky about the use of notation because it's very important to say exactly what you mean. So the sample space is the set of these outcomes, which I'm pretty much always going to name omega. But basically, I just write down those same outcomes I wrote down, except I put these curly braces around them now, and now it's a sample space. Okay, so these are the outcomes. They're just the things in the sample space, and the sample space is the set of outcomes. So then just to practice using notation, so I can write something like this, TH, that is something in omega, so that's fine to write. So is HH, so I can write that. That makes sense. what's not in there? I don't know, 52, that's not in there. Right, there's no 52 in there. And then perhaps a trickier one is this. T, just flipping a tails is not in omega, because omega consists of the outcomes of flipping 2 coins. And so this is definitely good to write because tails is not possible from 1 coin flip. So we have to take the list very seriously, very precisely. There are only 4 things in here. These are the 4 things. None of those are exactly, has to be exactly the same, just this, right? They're different. There's a T like in some of them, but none of them are just a T themselves. Okay, so just be aware of things like that. And then one final note about sample spaces, just don't forget the sample space must consist of all the outcomes of the experiment. So again, we cannot leave any out. They all got to be in there. They all got to be accounted for. Okay. Basically, the thinking is that we need to express everything that could possibly happen so that when we talk about probability, we're not going to leave something out that, or so it wouldn't make sense. You need to account for everything that could happen when you're talking about probability. So we got to make sure not to forget. Okay, let's do another example that's perhaps a little more tricky. So now let's roll a pair of dice instead of 1 dice. And again, one after another. And then we record the results. So there's going to be 36 outcomes. Maybe you can already see why. But this time it's a bit trickier to write them down. So last time when I had one thing after the other, what I did was just write the letters to represent the 2 things. So I wrote HH to mean heads, then heads. So here I'm not going to write 1, 1 to mean I rolled a 1, then another 1. Why is that bad? Well, because it looks like 11. So it's not going to be clear what the outcomes are if I use this as my notation. So instead, let's just use ordered pairs so that things are more clear. So I'm going to say 1, 1 instead. This will mean that we rolled a 1, then a 1. So I could have done this for heads and tails, but it wasn't really necessary because it's already clear if you just write HH what's going on instead of H comma H in parentheses. But it is necessary for numbers because otherwise it's going to look really weird. Okay, so then what is the sample space? Well, it's going to be pretty big because it's got to have 36 things in it. And those 36 things are each ordered pairs. So 1, 1, that's one thing. So there's a whole bunch of commas in here because the commas also separate the elements or the outcomes. So that's one outcome. 1, 2 is another outcome. 1, 3 is another outcome. So this will go all the way up to 1, 6. But then I could have started off by rolling a 2. And then I sort of get the same thing going on in the second coordinate until I go to 6. And then I go all the way until I basically just get 6, 6 at the end. So here I'm not going to list everything. I'm going to use ellipses. So these just imply the rest of the the outcomes. So I don't have to spend so much time writing, because otherwise it'll take forever to write all 36 things. It even takes forever just to write this much. So that leads me to even better notation to make this kind of thing faster, which you can use if you want. So set notation provides quicker options. So one thing we could do in set theory is you can specify the type of thing in the set in general first. So you could say, well, what kinds of things are in this set? They are all ordered pairs. So I'll say the things in here are ordered pairs, and I'll just put variables in place, and then you say what those, you be more precise, you say what those type of things obey, or you can think about these as like constraints that tell you exactly what's in the set. So here, M can range between the numbers 1 and 6. So you could say 1 is less than or equal to M is less than or equal to 6. That tells you everything M could be, and then N is the same thing. So it's much faster to write it like this, and it says the same thing. These are all the coordinate pairs that come as outcomes of rolling a pair of dice. Okay, so then just to practice notation some more, we can say things like this. So I could say like 4, 6, that's certainly in here. Or 3, 2 is in here. Or I could say 10, 17 is definitely not in there. So it's not in there, even though it's a coordinate, it doesn't fit in these constraints. So that's why it's not in there. But then just the number 4 is not in there. And it's like even worse. It's not even the right type of thing. So 4 is not even the right type of thing to be in there. Meanwhile, these just, although 10, 17 is the right type of thing, it's not in the constraints. So there's like 2 ways you could not be in the set, and these are the 2 ways. Okay, so then moving towards probability a little bit more. So far we haven't really talked about probability much. People like to understand the probability that an outcome, so something in the sample space in the list, will occur for an experiment. So this is where, like in high school, you see questions like, what's the probability of rolling? So in our language, we would say like rolling a 2, 3 with a pair of dice. But in high school, they would say like, what's the probability of rolling a 2 and then a 3? But that's really just saying, what's the probability of getting one of these outcomes in this set? And you would understand it as, well, there's only one of those in this set, and there's 36 total. So it's going to be 1 out of 36. That's how you understand it in high school, typically. But then they get more fancy and they ask about probability of, instead of just outcomes, events. So these can include more outcomes than just one. And so this is like saying, what's the probability of rolling a 7 with a pair of dice. And then you go in here and you say, well, there's a few ways to get a 7. There's the 1,6, but there's also the 6,1. There's the 3,4, the 4,3. There's a bunch of ways. And so you count them all up and there'll be 7 of them. And you say 7 out of 36. Or wait, no, there'll be 6 of them. So you'll say 6 out of 36 for that reason. So we're not going to worry about probability too much. More we want to distinguish right now between events and outcomes. So let's define it. So often in this class, I'm going to write definitions. In this way, I'm going to write the word def, and then I'm going to just write the definition after that, because I don't want to write the whole word definition every time. It takes too long. Okay, so what is an event in this class? It's any, I'll put this in quotes because we haven't said what it is yet, any subset of a sample space. Meaning a subset is exactly what it sounds like, meaning a set of outcomes coming from the sample space. So it can include any number of outcomes from the sample space. It could include 7, 100, it could include one of them or all of them. Those all count as events. So let's see some examples. So let's do just rolling 1 dice again. Experiment of rolling 1 dice. So then we already know what's omega. It's going to be just the numbers 1 through 6. So what are some events? Well, they are themselves sets. So they got to be written in curly braces, and that's because they are subsets. Subsets are themselves sets, so they have to be written in these curly braces, and we can name them letters. We typically name them capital letters. So I might name this first one A. And so here I just put some of the things from the outcomes in the sample space. And so A is a subset of omega, so A is an event. So this might be the event of rolling an even. You might ask in a high school class, like, what's the probability of rolling an even number with a roll of 1 dice, as opposed to just asking, what's the probability of rolling a 3 or a 4 or a 5, all individually. So an event allows you to think about more than one thing at once. So that's an event. So is this, 5, or this. You could just have one thing in it, which is kind of weird. So it's an event with one outcome in it. That's perfectly fine. It still counts because it's still a subset. It's still a set consisting of things coming from omega. So as long as it does that, then it counts as an event. Even the whole thing itself is an event. It's an important event. An event where something has to happen. So that's going to be important later. So these are all events. Sometimes we write them in words. So this first one, A here, you might want to just say something like this, roll an even. And as long as you're describing the same set in words, then it's okay too. So even this one, you could just say, roll a 4 if you wanted to. As long as you're describing the same set, then it's the same event. Okay, so those are all examples of events. What's not an event? Well, something like this is not an event because 10 did not come from the sample space. In other words, 10 is not an outcome of the experiment. So there's no way that you could ever roll a 10. So we're not going to count a 10 being in a set as allowable. So this is not an event. Even though 1 and 3 are okay, 10 ruins the whole thing. So it's not an event. Okay. So there is some notation for this stuff for subsets that we're going to use. So you write one set and then you write another set. And you put this sort of curvy less than sign, sort of just like a C. You could look up online a subset notation to see a better drawn one than I can draw, but it just looks something like this. And this means A is a subset of B. So to think about our definition of events, let's do it down here actually. So an event A has the property that A is a subset of omega. So if you write this, then you can say A is an event. Okay, let's think about another example. So let's flip 3 coins this time instead of 2. So then there's going to be 8 outcomes. And we can use our H notation. So we just write 3 H's to mean that I flip 3 heads in a row. And then I can just sort of list them all out here. The last one could have been tails. This one could have been tails instead. Whoops, that's not the order I want to do it. And then this last, and then the last 2 could be tails. And those are all the ways to flip 3 coins starting with the heads. But I could also start with tails and then sort of do the same type of pattern here to figure them all out until I get all of them. Okay, so this is the sample space for flipping 3 coins. So let's say some facts about it. So I can write events now. So like this is an event. With 3 outcomes in it. And it's because it's a subset of omega, because everything that you see in here comes from omega. I'm not just getting random things from somewhere else. They all come from omega. That's why it's a subset of it. What else? Oops, stick to the same color. So it's one fact. Here's another fact. You can have a subset with just one thing in it. So this is another event. And again, so B is a subset of omega. If I just write HHT with no curly braces around it, that's an outcome. And now that's because HHT is an element of omega. So be aware of this difference of these notations. And be very correct and precise when you use these notations. These are 2 different types of things going on. One is a subset, one is an element. You got to use them correctly. Let's do another one. So C equals this, H comma T. This is nothing, right? This is not an event, and it's also not an element. Why is it not an event? Yes, it's a set, but it's not a subset. So you could write C is not a subset by crossing out the subset notation of omega. And that's because if you look in this set and you look and you see there's an H and there's a T, those are the 2 elements. Those are the 2 outcomes. Neither of those 2 things are in omega. None of these things are exactly H or T. they have more than one H and T, they're not H or T alone. So none of these are H or T. So that's why none of these are in omega. Okay. So let's see. So another way to say it is, or because H is not in omega, and neither is T. Okay, just to use the element notation, but we're saying the same thing. And we can talk about events in relation to each other. So if you have two events, so let's make A be this one, and B be this one. THT. Then they have a relationship to each other, which is one is inside of the other. So if you notice, B has everything that A does, plus a little bit of extra. It's got one extra thing. So we can also say that A is a subset of B and make like a little chain, and that's a subset of omega. They're both subsets of omega. They're both events. So these are both events, but also one is inside of the other because one contains all the outcomes that the other does, plus a little bit of extra stuff. Okay, so this leads to another definition. When this type of thing happens, we want a name for it. So we say an event occurs. So what does it mean for an event to occur? It's going to be sort of what you think it is. It just means that when you actually do the experiment, if the outcome of an experiment, so when you do an experiment, you get outcomes. And if that outcome is in the event, then that's what it means for the event to occur. So we say an event occurs if the outcome of an experiment is in that event. So sorry, that definition is not what's relating these two things together. Like I said it would, the next definition is what will. So in this last example, if A occurs, then so does B. Why is that? Well, if we look at the two sets A and B here, so we're still looking at this example, if A occurs, that means that the outcome had to have been one of these two things. So if A occurred, then the outcome was one of these from the experiment, but those are both in here. So B must have also occurred because the outcome of the experiment was in B automatically. And that would mean that B occurred as well. So we want a definition for this kind of thing. And what we do is we say event A implies event B when, how did this happen? When A is a subset of B. And it's because A occurring automatically, or let me say it like this, A occurring lets us deduce B occurs too as a result. Oops. And it's just because all the outcomes in A are in B. So, oh wait, so yeah, so if A happens, then B has to automatically have happened because A happening or occurring means that an outcome from A was the result, but those are all in B2, so B must have also occurred. Okay, let's do a little example of this. So let's use a smaller set as our sample space. We'll just do rolling a single die again. And let's think about 3 events together. So if I have 2, 4, I have 2, 4, 6, and I have 1, 2, 4, 6, then I can say A implies B, because if A occurs, that means I rolled a 2 or a 4, which means I automatically rolled a 2, 4, or 6, because I definitely rolled a 2 or 4 first. But I could also say B implies C, because if I rolled a 2, 4, or 6, that means I definitely rolled a 1, 2, 4, or 6. And I could also say that A implies C too, because rolling a 2 or a 4 implies that I rolled a 1, 2, 4, or 6. And these all can be written as, well, that's because A is a subset of B, or because B is a subset of C, or because A is a subset of C. So either way you want to write it, they're really saying the same thing. Okay. So as I said before, one important event is the sample set itself. So it's important because it's the only event that must occur. Because when you do the experiment, this is the only event that has all of the outcomes in it. And so when you do the experiment and an outcome happens, that means that this set has to occur. So it has all the outcomes. So anytime the experiment happens or is done, the result will always be in omega, so omega will always occur. Okay, and that's going to come in handy when we think about probability. So what's the probability that the event omega occurs? It better be 1, it better be 100% of the time. Otherwise, you forgot to put one of the outcomes in there. Because it has all the outcomes, it must always occur when you do the experiment, so it must have a 100% chance of happening. Okay, so let's do one more example, a bit more wordy of an example, just to see how experiments can be sort of vaguely fit into other things that don't seem like it at first. But suppose we choose a floor and a wall color. So then the floor options are wood or black, and the wall options are white, blue, and green. So then choosing a combination can be viewed as an experiment where the sample space is just the list of all the possible combinations. So in this case, the order of the combinations matter because you're choosing a floor first. So one possible element is wood, comma, white, because the floor can be wood and the wall can be white. But notice this is not the same. It's different from white comma wood, which is not in there. It's not going to be an omega because the floor is being white is not an option, and the wall being wood is not an option. So this is one element of the sample space. What's another? Well, you could have wood, comma, blue. You could have wood, comma, green. And then you could have the same three, but now with black as the first coordinate. So you could have black, comma, white. You could have black, comma, blue, and black, comma, green. So these are the 6 elements in here. 1, 2, 3, 4, 5, 6. So you do have to be careful about order depending on the experiment. So depending on experiment, you might have that x comma y is in omega, but y comma x is not. So you do have to be careful. Okay. So the last thing I want to do is just a little bit of set theory practice. And then next time we'll talk about probability. So let's just think about some sets. So let's have a set called X. It'll have 2, A, and Z in it. And let's have a set called Y, which will have weirder stuff in it. So you can have sets of sets. So you can have a set that has the set 2 in it instead of just the number 2. Or you could have X comma Y. Let me use different letters actually, because I use that. Let's just use A and B. So we can have sets like this. So let's sort of just make a true false column to see types of things we could write. So for example, what's something that's true? 2, that is an element of X, but 2 is not an element of Y. So I should say actually this is false. So 2 is not in there because there's no just 2 as one of the 3 elements. This is not the same as 2. The set consisting of 2 is not the same thing as the number 2. So that would be false to write. It would be okay to write this. That's fine. So what else? Let's see. I could write that 4 is in Y. I could write the set consisting of A, B. That's in Y. I could write Z is an X. That's fine too. So what about subset notation? So I could write the set consisting of 2 and A. That is a subset of X because those 2 things are in X. I could write the set consisting of 2 is a subset of Y because it's a set that has stuff from Y in it. So that one's a bit weird to write. And I could write the set consisting of 4 and the set A comma B. That's also a subset of Y. That's fine. Because 4 and the set AB are both elements of Y. So together they can form a subset. So what's some like bad stuff to write? Let's see. Well, I could try to do subsets on this side too. So I could say like something bad would be like saying that 2 is a subset of X because it's not, it's an element. Another one would be this. This is not a subset of Y because it's an element of Y. So I need the extra curly braces like I have over here to be a subset. Okay, so just be aware of things like this and be very careful with this notation. Okay, so that's it for today. See you all next time.